Thanks. I'll just share my screen. And I hope you guys can see that.
We do.
Great. So yeah, I'm going to talk about the Holocene framework that I've been working on recently, but I'll start with a new framework that I've just submitted for the LGIT, which both will hopefully be useful for those of you working with proxy records in the terrestrial and marine realms that use Tephras constraints sort of to synchronize records. So yeah, I won't mention more about chronology of ice cores, since Sue has done a great job of that this morning. But I'll just say that yeah, so the ice core volcanic layers that we find, they're obviously given a date based on the chronologies from the ice cores. We find volcanic ash mostly as cryptotephra layers in the ice, so that's basically like hidden layers, you could say, invisible to the naked eye, that you really need to search for. And yeah, so finding these layers in the ice, especially below the Holocene, really contributes to the reconstruction of past volcanism frequency. And this is particularly important for a long-term perspective, especially in records where proximal materials have been eroded away, such as Iceland, which was covered in ice caps in the glacial period. And yeah, there's not much of a record anymore on the terrestrial. So I find records of volcanism, particularly from Iceland, obviously in Greenland, because it's so local to Greenland, but also there's other volcanic influx of tephra from regions, Kamchatka and North America. So I'll touch on those a little bit, mostly in the Holocene section. So just to reiterate, on the left you have a map of Greenland and the main ice core drilling sites, and these are the cores that I've used to build my tephra frameworks. Mostly North Grip, I have to say, and also Grip and Neem, and a little bit with East Grip and Recap, which are the most recently drilled cores. And in fact, East Grip is still being sort of extracted as we speak. We've been delayed for a couple of years, obviously through COVID, which cancelled our field season in East Grip. We still have about, I don't know, 700 meters to go, I think. So hopefully that will resume this year. But yeah, so used a number of cores to try and maximize the cryptotephra identification in Greenland, because we find that different tephra layers, when you compare different cores, you don't find the same layer in all the cores. So it's good to use a number of cores to try and maximize the number of volcanic events that you can find in the record. And I started this work during my PhD, so it's been over like 10 years now, to build these frameworks, starting at Swansea University and then through the Ice to Ice project, which started with the LGIT work and more recently the Holocene framework that I've been constructing. So yeah, when we find tephra layers in the ice, we get a geochemical fingerprint through electron probe microanalysis and laser ablation ICP-MS for the major and trace elements. And with this data that you can compare to reference material and then try to find your sort of source region and a particular volcano if the reference material is there and you've got a match. And once you've built basically a chronology or stratigraphy of these records of these different tephra layers in the ice, you could then draw out key marker deposits, for example, those with really unique chemistry or really unique origins, or those that fall on the transitions of different climate events that could act as constraints. And then try to, I guess the aim is basically to try and then, once you've got these really nice records in Greenland, to try and trace some of these tephras in other records that could help, transfer the time, the age from the GICCO5 ice core ages to sort of other records in the terrestrial or marine realms. And then once you've done this, you can also, if you have a set of tie points that you've established through between the ice core and different records, you can start looking at sort of potential leads and lags in the climate system. Also, you can look at individual eruptions themselves to see if they have any sort of climatic impact. And we've seen, with recent results from Joe McConnell looking at the Okmok eruption, that there is an associated climate impact with some of these eruptions. So in the Northern Hemisphere, there's a lot of potential sites that contribute their ash to Greenland. We find that we don't see in Greenland any events from the Mediterranean region, probably due to the sort of prevailing wind conditions. But we find, obviously, Icelandic eruptions are dominant, but there's also a contribution, especially in the Holocene, from centers such as Kamchatka, North America, Japan, which is really useful as well. These distal records that have the potential to connect, Greenland to deposits really far away in different, continents. So going back in time, before I constructed, I'll start with the late glacial interglacial transition framework that I've created. Before this work was started, there were around about 15 deposits that were found in Greenland. So on the left, you've got the North Grip isotope curve, and then you've got the tephra layers that were found by Annette Mortensen, Carl Grunwald, and Schuan Davis. There are about 15 of those. And then in the middle, you've got other regional tephras that are key in this period. So this period, this section in the middle from different centers were those that I was aiming and trying to seek out through my sampling strategies for Greenland. Some key tephras included the Borbol, Lacasay tephra, for example, Glacier Peak from North America, as well as more local Icelandic eruptions such as the Vede ash. Just to quickly talk about how we do find the tephra deposits in the ice. So these are 3 different ice cores: North Grip, Neem, and Grip. On the right side, I started with Neem as kind of a patchy sampling strategy based around electrical conductivity or acidity spikes in the ice, which wasn't so what's the word, successful. So I then turned to more continuous sampling strategies for North Grip and Grip, and I found a lot more events through this sort of laborious, time-consuming method. A lot of sampling strategies before had relied predominantly on sort of either visible tephra layers in the ice or the acidity peaks or sulfate peaks. And we found through our work that this isn't always a reliable method, because you get tephra layers with peaks, as you see on the left hand side, but you also get peaks without tephra layers associated, and you also get visible tephra layers with no peaks at all in the chemostratigraphy. So the continuous sampling has really allowed us to find a lot more tephra layers than before. But it is a time-consuming method, and maybe not always the most appropriate technique if you have a specific interval in mind. But anyway, in order to extract the tephras from the ice, you start with cutting a strip off with a bandsaw, then melting it, centrifuging it, looking at preparing slides that you look at under the microscope, and any that you find with tephras you take away for geochemical analysis. It's quite hard to get a good data set and analyses from these ice core tephra grains, because typically they're really, really small. So typically between 5 and 50 microns in diameter. Many are full of vesicles, so that it's hard to find a surface to analyze with the probe, which has around about a 5 to 8 micron beam sort of diameter. But it's important to analyze as many of these grains as possible. So this is just an example of what we're working with in the ice. Or maybe it's around 10 microns in side to side, and you can see this sort of contamination spot from the electron probe in the center, and you're just kind of trying to fit this onto a grain, an individual grain, get analysis. So it sometimes works. But even with a lot of results even with a lot of layers that I wasn't able to analyze, I was able to build up a really comprehensive record for Greenland over this period. And thankfully, it's just submitted. So in the next few months, you should be able to have access to all of the depths and the compositions for each of the tephra layers that I found in each of the 3 ice core records for this period. So I really hope that this will be, a useful starting point if you work with high resolution terrestrial and marine records that have, a good proxy record associated with them, to try and find some of these tephra layers to tie to Greenland, and then with the aim of looking at leads and lags in the climate system of these rapid transitions. So what we have on this diagram here, on the left hand side, again you've got the isotope curve from North Grip, then you've got North Grip, Grip and Neem ice cores and associated isotope records on the depth scales. And against the depth scales, I have marked in either blue or green the tephra layers for the individual cores that I found. So the blue lines denote the basaltic layers, and the green, the rhyolitic. And over this interval between the 3 cores, I found 64 new different tephra layers. And many of these correlate between the records. And many of them sort of are located stratigraphically on the boundary of different transitions, for example, within GI1, equivalent to Boeing LMR. So I created a huge amount of data, which will be available hopefully soon. So the first step is obviously to figure out the classification of the material that you're working with, or the rock type, through this silica alkali task diagram. And once you have this, you can then try to compare your data to the same sort of rock type, to the same material in other records that are similarly dated, and try and find correlations. So just a takeaway from this framework that I've created in collaboration with Swansea University and many of my colleagues at Copenhagen. So before this framework, there are only 15 published tephra layers for this interval, between 11 and 17,000 years. And this framework now brings the total to 50 individual eruptions. Many of these are found in multiple cores, so there's 20 ice-to-ice correlations. What's really nice is that it's from the tephra layers that I find in this interval from different centres in Iceland, with many different compositions. Basaltic from Katla, Grimsvotn, Vidbotn, many rhyolitic as well from Órfjökull. The framework is dominated by basaltic layers, but there are sort of rhyolitic deposits punctuating the Greenland Interstage 1 GS 2.1 as well. And we have just 2 non-Icelandic tephras, one from Japan, from Tawado at 15.7 thousand years BTK, and another from Mount St. Helens in GI1C. We don't find the Lacusate tephra, unfortunately, in our records. So the significance of this new framework is that, first of all, it improves the regional tephra stratigraphy, which is a goal of INTERNET. It improves our knowledge of the eruption history, particularly of Iceland during this period. It provides new tephra constraints over key LGIT climate events, including the Holocene transition, which I'll talk about in a minute. And I've been able to correlate 6 deposits to other terrestrial and marine tephras that have already been published in the Northern Hemisphere. But the remaining 44 are unreported in other terrestrial or marine records. So this is where it holds huge potential, this framework for trying to trace these tephras in other records. As I mentioned, some of these tephra layers fall really close to transitions. If you look on the left-hand side, so this is the Neem core, and I found a layer from Hekla, which occurs just a few years after the Holocene transition in the ice core, which will be really useful, obviously, if you can find this Hekla deposit in other records, to explore the relative timing of this transition. regionally. And on the right side, you can just see the sheer amount of tephra layers in GI1. So they all have different compositions. So hopefully, yeah, these can be really useful if they can be found in other records. This is just a summary of the most, I think, 23 most useful tephra layers that I figured out based on, unique chemistry, location, whether they're found in more than one core, whether they correlate to other records. As you can see, I've correlated to a number of records such as the Vede ash that's found, widespread in Europe, Mount St. Helens, the boreable tephra from Iceland, and some others in GS1 from Tawada, and a new one with a boreable type material in GS2.1. There's also a suite of Oreshokel type eruptions that occur around about 17,000 years ago. One which is particularly useful that seems to that ash grains seem to occur over 22 years in North Grip, which I don't think has been identified proximally in Iceland or in other regional archives, which will be really useful, I think. I also compared some of the tephra layers that I found, especially the ones that correlated to other terrestrial marine records, to their chemostratigraphy, just to see, how these events look in the against electoral conductivity measurements or dielectric profile that measure the acidity or impurities in the ice, as well as sulfate. So there's only really a good sulfate record for North Grip in this case. So that's what I've compared to here. But we find that only, just over half, or I think it's missing at the top of my screen, but I think it's about 59% of the tephra layers that I've found here from Iceland occur with coincident ECM or DEP peaks, and around about 45% with sulfate peaks. And overall, the Icelandic events have a low signal to background, so it's difficult to sort of characterize the signature or representation of these Icelandic events in the Greenland chemical proxies. So it's difficult to get an idea or sense if they have any long-term climatic impact. We also find, evidence of local differences. If you look in the middle row, you've got two E and F. You've got Tawada as found in North Grip and Tawada tephra as found in Neem. And this Tawada tephra was a bipolar event, so it's found in the chemistry of Antarctica as well. And you can see in the sulfate and ECM records, there's a huge peak in North Grip, but it's completely absent in some of the records from Neem, which is a bit surprising. So I'm just going to touch on some of the Holocene stuff that I've been working on recently. It's not yet ready for publication, but here are some initial results. And of course, if you have anything that's interesting or would like to compare, then I'm always up for sharing data and collaborating. So get in touch with me afterwards if there's anything that jumps out that you would like to talk about before this is published, because it might be a couple more years. But I've mostly focused on a sampling interval in North Grip between 5,000 and 9,000 years. So if you look on the left-hand side, you've got the GICC05 timescale and North Grip oxygen isotopes. And this is a combined, and I've put all of the tephra layers that have so far been found in other studies in dashed lines, and the ones that I found from different ice core records, sort of as a composite diagram. And then you've got North Grip recap and East Grip on their depth scales and the relevant, and the tephra layers that I've recently identified with bars sort of going down on each of them. For North Grip, you'll see that I've got a lot of tephra layers, and this is just due to the fact that I continuously sampled from about 5,000 to 9,000 years. There's a break in the middle, and that's where another team, Shu and Davis from Swansea, has been sampling. So in a few years the combined frame will hopefully be a really detailed one. But the North Grip one, was continuous sampling. Recap in the middle, that was based on visible layers and key tephras. And East Grip is like a work in progress. Most of the tephra layers identified here from field observations. So for example, those that were visible in the field, or by chemical peaks that we identified in the field when we were cutting the ice, and we were able to sort of separate these bags of ice out for immediate processing. So these two cores have a far less tephras associated, but it doesn't mean that there aren't tephras there. They just haven't been analysed yet. So just some initial, take-home messages from this initial tephra framework of the Holocene. Before this, there were around 13 published layers for the Holocene. With this work, now there's around about 60 individual deposits, or that takes it up to about 70 in total in different Greenland records, incorporating other people's work. And many more layers, as I said before, will come from Shu and Davis's group at Swansea, who've sampled different intervals to I have. Most of the events are from Iceland. There's many basaltic capillary layers throughout. There's key recent historical deposits such as the settlement layer, Hekla 1104, Orifsjökull. And interesting, 20 deposits constrain the 8.2 and the 9.3 cold events and can be used, to inform sampling of intervals for, different marine or terrestrial records. And 12 are from the Northwest Pacific region, which is quite interesting because it's very different from the LGIT, where you find basically Icelandic tephras throughout and only a couple of non-Icelandic tephras. We find that there's, more varied sources in the Holocene. And I'm not entirely sure why that is, if it's, just increased volcanism after the glacial period, or different wind patterns that were restricting the deposition of different tephras from different regions in Greenland before the Holocene. So that needs further investigation. One of the layers I've already published is from Kamchatka, a few years ago now. So that one's already out, and supported by trace element and major element data from proximal material. So that kind of started, kicked off the published Holocene record that I've been working on. There's other key deposits, as I've mentioned, such as Orifsjökull, which I found in a number of records. Some other highlights include a couple of Mazama type deposits in close succession in Eastgrip, which is quite an interesting finding. I think in the proximal records close to the Mazama volcano, they have had a suspicion of that before, but it's interesting to find these two events in the ice. And a similar thing for Saxon-Nevatten. There's like a closely spaced couplet in Eastgrip with very similar chemistry. These are based on visible layers that, as you can see here on the right, there might be even more cryptotephra layers with a similar chemistry, similar to Saxon-Nevatten, around these intervals if we look a bit more closely with some continuous sampling. The one thing I found really interesting and a bit surprising was the number of Kamchatkan tephras that I found over the 8.2 sort of to 9,500 years in close succession. Sorry, I've had to block out the names of them, but because we're working on a paper at the moment. But it's really, that's really interesting because we don't find any Kamchatkan tephras before the Holocene, and we know that Kamchatkan tephras, Kamchatkan eruptions were also prominent, for example, 25 to 45,000 years ago, and we don't see them in the ice yet until the Holocene. So that also has maybe implications for, for the main atmospheric conditions that perhaps blocked the transport of these tephras up to Greenland until the Holocene. One of the tephras from Kamchatka has a huge signature in the sulfate record, and it's also found in Antarctica. If you have a look at the one listed 8.5 thousand years. And I guess the take home here is that my colleague GMI from Copenhagen has been calculating the total volcanic sulfate deposition from this event in Greenland and translated that to a global forcing sort of value, which is at least 4 times as big as the Okmok event that was recently published that had this societal impact due to climate cooling, also bigger than other key eruptions such as Tambora and Laki. And my colleague at Copenhagen, Johannes Lohmann, has also been looking at some of the climate impacts of this eruption. So I guess the take home is to look at maybe the red line on this diagram. We found negative isotope anomalies in each of the Greenland isotope records, oxygen isotope records, which he converted to say was at least 1.2 degrees of cooling, based on some analysis that he did, which is also really interesting. And it just shows that, as well as using the tephra layers as a chronological tool, some of these tephra layers also have the potential to affect climate over a decade, quite significantly. And that's also another aspect of the work that we'll be exploring in a new paper with these Kamchatkan events. So I guess the final thoughts just are that, as we resolve climate signals in our records in more detail, there's demands for more precise and accurate chronologies. And hopefully the tephra deposits that we find that constrain these important events can help establish tie points to different regional records, and eventually synchronize different records and assess these leads and any leads and lags in the climate system, or not, maybe they're synchronous. This work involved a lot of collaborators, so I'd like to say thanks to this big list of people here and many more that I haven't included. So thank you. And any questions?
Thank you, Eliza, for a very nice talk and some amazing work on extending the tephra framework for the Greenland ice cores. So if there are any questions, feel free to raise your hand or write your question in the chats. I'm just going to check if there are already questions there. Not yet. Oh,
not yet.
Nick has a question.
Hi. Yeah, go ahead, Dirk.
Okay. Thanks for the talk. Very interesting insights into what's going on with the ice core crypto tephra chronology. I have a question. You showed this comparison between the crypto tephra identifications you did and the sulfate and conductivity records. And you quickly mentioned that the signal to noise ratio for Icelandic eruptions is very low, but is there any correlation with the intensity of that peak and the proximity of the eruptive centers, or the assumed intensity of the eruption? Or is this
it's something I haven't looked at, and I think it kind of raised the question of how do we kind of characterize these Icelandic events in Greenland when that they provide such small signals. And I think it will be good to look at the shape of the signals through the different records, such as the sulfate and acidity, but it's something that I haven't considered yet. But I think it's something that needs to be looked at in further detail now that we have these records of Icelandic volcanism. It's further work to do, but I don't have any answer at the moment, I'm afraid.
Thanks.
I see two questions. Maybe first from Olaf. Go ahead.
Yeah, thank you both for your talks. It was very fascinating. I'm not a geoscientist, but an archaeologist and working with the Paleolithic, and have always had an interest in these high resolution records. My question goes to Eliza, as whether or not you can figure out whether or not the Icelandic volcanoes are mainly within certain seasonal layers. So like when seasonally the wind system has changed in the favor that the tephra could be deposited in the ice core, or if it's just random.
Yeah, that's a good question. I mean, from my work, I think you could delve into that with more recent records. You can certainly take some snow pit samples to figure out the month where certain eruptions sort of took place, but my sampling interval is a bit wide to try and narrow that down in this context, I'm afraid. But it certainly can you can figure that out through sort of snow pit studies, but I haven't looked into that actually.
Thank you.
Yeah, and just my resolution is too low to figure out the season at that depth. But yeah.
I think we have a question from Danielle. Danielle.
Hi, Eliza. Yeah, thanks. That was a really great talk. I just was curious about when you mentioned that you're finding different cryptotephras in the different ice cores. I wondered if you had an idea of what was causing that. Is it a concentration issue? If you're finding, are you more likely to find lower concentration tephras in grip, for example?
Yeah, so actually between North Grip and Grip, it's quite similar, but we find that we do see lower tephra numbers of individual counts in Neem, for example, which is further away, and the tephra grains are also slightly, maybe about an average of 5 microns smaller, and this result also mirrors work done by Anna Bourne in the glacial period, who found a similar result. Yeah, so we do see these regional differences, but we also find that in some cases it's the opposite. So you could have huge amounts of tephra in Neem. It doesn't happen so often, and less in North Grip. Maybe it just depends on the depositional plume, because I think it can be actually quite patchy in its development from the eruption site. Yeah, it's something that probably also needs further look into as well. But we do find that those situated closer to Iceland have bigger grains and larger concentrations of individual counts.
Great, yeah, thank you.
Yeah.
I see a question from Lawrence. Go ahead if you still have a question, at least.
But anyway, I just hope that these two frameworks, I mean, the one that I've just submitted will hopefully be out in a few months and can be a really useful starting point for people trying to establish tie points to Greenland.
Can you hear me now?
Yes.
Okay, sorry. Yeah, I used the wrong microphone. Thank you so much, both of you. Eliza, the lack of Kamchatka tephra in the glacial, do you think that can be interpreted as Greenland being more isolated in weather, in the sense of weather in the glacial?
Yeah. You know, I'm not entirely sure. I think it's like a whole, I've been thinking about it, it's a whole question, and it's a whole research area in itself, whether maybe you've got these, maybe it's the interplay between something like the Aleutian low and the height of the ice sheet in the glacial maximum as well. So yeah, it's a bit of an unanswered mystery, but I think it must have something to do with the circulation in the glacial compared to, and the height of the ice sheets. Also on the northern hemisphere, North America, as well as Greenland, that changes the dynamics and compared to the Holocene. But that's just kind of speculation. I haven't done any work into it, but it does raise those questions as to what are the mechanisms that, you know, because there were big eruptions in Kamchatka that they've been found in marine sediment cores. And Kamchatka it had ice fields, but it didn't have ice sheets on top of the volcanoes. So it's a bit of a mystery, but it must be something to do with the circulation changes.
Thank you.
Yeah, so we're going to start the discussion also, so people can also start asking questions for Sune. We're also a bit past time, so if people need to leave, feel free to leave, but for all other people, feel welcome in the discussion. And yeah, you can just open up your mic or camera or write a question in the chat, and I won't be managing the questions anymore.
Yeah, I see a question from Stefan.
Yes, I have. So thanks both for your really nice talks. Very interesting. Perhaps, so I have many questions, but I will focus on one. perhaps trying to connect both talks as well. Do you think you could use your tephra framework to refine the chronology? I mean, to kind of reset your counting, or just check if the counting is doing well?
I think maybe it's maybe used as like an independent validation for the counting, especially maybe useful in periods such as Suna said around GS2, like 22,000 years ago, where there's fewer tephra, fewer ECM match points between the different cores, but typically not so much, apart from in this sort of interval. Would you say so, Suna, if you're still there?
I am.
Stop
Yeah,
recording.
I am, and I agree.